Morning to all our attendees joining us from Europe, and a warm welcome to those joining us from Asia. We are thrilled to have you all with us today for our webinar, eMMC and SD3.0, UHS-II Electrical and Protocol Overview with Test Solutions. My name is Pranav and I'll be your host for today's session. We have an esteemed presenter with us today, Mr. Godfrey Coelho. Godfrey has over 25 years of experience in the test and machines industry. During this webinar, Godfrey will share his knowledge and experience on eMMC and SD3.0 UHS-II protocols and their test solutions. We encourage all of you to actively participate in the webinar by posting questions in the Q&A session. And the last 10 minutes of the webinar is purely devoted to answering your questions. Please note that the webinar will be recorded and a link for the webinar will be sent to all the attendees after the session. So if you experience any connectivity issues during the webinar, don't worry about it. You won't miss out on any valuable information. Now, without further ado, I'd like to hand over to our presenter, Godfrey. Over to you.
Yeah. Good afternoon, everyone. Can you hear me well? Okay. So I'll be taking you through about eMMC and SD protocol as well as electrical measurements, and also what is the solution Prodigy Technovation is offering. So today's agenda, just to give you some introduction about Prodigy Technovation, because many of you may be new to Prodigy Technovation. And then we talk about the overview about eMMC and SD interface, how they are different and what are their performance and specifications. What are the electrical parameters and what are the different protocol packets. Then we discuss about challenges in electrical validation as well as in protocol analysis, and how Prodigy Technovation is offering the solution to address these challenges. So Prodigy Technovation, we started this company way back in 2009 in Bangalore in India. We were initially started with developing application software for the oscilloscope like Tektronix, mainly decoding the protocol decode for eMMC and SD and many other interfaces. Then we slowly graduated and we thought many customers asked us to provide a standalone protocol analyzer. And eMMC and SD is one of our first protocol analyzer we launched some time back, and it has been well received. Today, Prodigy Technovation has a broad portfolio of products, a team of 60 engineers working in Bangalore, providing customer supports and developing new products. And we do have a distributors throughout the geography, in China, Japan, Korea, Taiwan, and in the Southeast Asia, India, and also in the European region. We have distributors. So if you need any of our products, you can reach out to our distributors. You will find their contact details on prodigytechno.com website. So we have a good client base. Majority of the semiconductor companies and the storage companies are our customers. We have been working with all the leading house customers like Intel, Qualcomm, Nokia, Bosch, SanDisk or WDC, Kioxia. Over a long period of time, we have a deep expertise in understanding customer requirement and providing a very valuable solution at a very reasonable price point to our customers. So our product portfolio will include from a very low speed, starting from I2C. We have a protocol exerciser and analyzer starting from I2C, SM bus, PM bus, and many other interfaces like the QSPI, eSPI, and all, and going all the way up to UFS 4.0, which is operating at 23.32 gigabits per second. Then we have a PCIe Gen 3, Gen 4 protocol analyzer in our product portfolio. So as well as we provide also oscilloscope-based protocol solutions. So based on your needs, you can choose how we want to proceed. So you can always contact us, any products, even if you don't find it in this spreadsheet on this slide deck, you can always free to contact us. Maybe there is new product under development which may meet your requirement. So let's look at the eMMC interface. eMMC interface as there are two components. One is a host controller, and then there is a target, which is a device actually. And the host controller and target is connected using a CMD signal, which is a command line where the host and device will exchange the command and response packets. And then there is a clock. The clock will be driven from the host, you can see here, and to the device. And then there are 8 data lines. And these data lines can be configurable depending on the use cases, like you get one line, 4 line, or 8 line, depending on your use cases, you can configure it. And during the read operations, right? So the command will be, the controller will be sending a read command to the device, and device will send the data. But the clock will be driven from the host device, and in order to clock to synchronize well, there is also a strobe signal which will go from the device to the host. So the data which is read from the device will be sampled using a strobe. So in overall, there are 11 signals to be monitored. That is a command, clock, strobe, and 8 data lines to be monitored. And then we have a VCC, VCCQ. This is a simple block diagram of a eMMC controller and eMMC device connected in a system. Okay. So the data lines are bidirectional in nature. Command line also is bidirectional. The clock is from host to device, and strobe is from device to host. Okay. Now, how does the command looks like? Now, how do you identify this command? As I mentioned, command will be sent over a command line. So it will start with the start bit going low, and then the high 1 bit. And then there are 6 bits are allocated for what type of command it is. Like, there are so many different types of command. Commands are used for reading a register from the device, writing into a register, or sending some tuning parameters, or different types of commands are available. The 6 bits are allocated for command, and then 32 bits are for argument. They will have maybe a logical block address and so many other different information. Depending on the type of command, these 32 bits will be coded differently based on the need. And in order to ensure that everything data is transferred accurately, there are 7-bit CRC value also is transmitted, and the end of the command is a high, 1-bit high will be transmitted. So overall, the command is a 48-bit in size, and also there are all the commands may not be assigned as on today. Some of those are reserved, and some of those reserved commands are used by vendors for making their own custom commands based on the need of the market. Okay? So this is how the command token would be looking like. Now here you have a response. Response is go from the device to host, right? And the difference here, significant difference, you see how do you identify is that the second bit in the token is actually logical 0. And then the content of the command response can be 48-bit or 136-bit, depending on the what we are sending it. Like, if it's a CID and CSP register value, then it is a 136 bits. Otherwise, it will be 48-bit, which will have information about different device status. And we can see that during the live demo, how those different device status will look like. And then we have a 7-bit CRC, and at the end, there is a logic 1 to indicate the end of the response packet. So this is the overall response token packet would look like. Now, how does the data is being transmitted, right? So as I mentioned, data can be the data bus can be configured as a 1-bit, 4-bit, or 8-bit. Now, when the data needs to be transmitted on a 1-bit, so it will send the B0 first and B7 at the last on the same line. At the end, there will be a CRC and then the stop bit. Okay, and each of these one data block would be 512 bytes. Okay, so you can send those data and look at the CRC value. When the data bus is configured as a 4-line, so the data bits of a byte are distributed over a 4-line. Like you can see here, the B0 bit will be transmitted on data 0 line, B1 on the data 1, and B2 on the data 2. So this is how a byte would be transmitted over a 4-line data coding method. And at the end, there is a CRC value and then there is a stop bit. Now, what is important is that the CRC value is computed based on the bits on the data 0 line. It is not on the combination of all the bytes, okay? It's based on the bits on the data 0 line. So this will help us, like, when we do some signal integrity analysis or protocol decoding test, if we find a CRC error in a particular line, we know that the rest of the lines may be working fine and maybe the bit data 2 may be having some trouble, and then that's how we would like to decode that and or maybe analyze that. Okay, so the CRC is computed based on the bits transmitted on the particular data line. Now here we have something very similar for 8-bit. So 8-bit data line. So with each data line will have each of the bits is transmitted on the line, and then we have a CRC value. It also supports DDR mode. So we can see here the data will be sampled on both the rising and falling edge, and you actually double the throughput by sending the data on a DDR mode. So this is how the is a difference between the SDR mode and DDR mode. But initial data will be like clock will be toggled. That data will be sampled on the rising edge. But once the data transmission takes place, it will be sampled using both the rising and falling edge. Okay. Now we have a different types of commands, the sequential commands. Like now, the first will send a command to the device, and the device will respond to that with the information as based on the command, and then the data will be transmitted on the data 0 or a 4-bit line or 8-bit line, depending on the requirement. Okay, and once the data is transmitted, the host can send the next command and the response, and this will continue to go on. Now, if the bus is busy and it will hold the line B0 line low for some amount of time, basically telling that there is no other activity to take place on the data line. So data stop operation takes place during the busy line of the bus. Similarly, we have a block write, like in case of a block write, the data will be transmitted, and then there is a CRC. So each data block can be 512 bytes in size, and so you have a busy line and then continue to send the data, so forth. And the busy line will be on the data 0 line. The rest of the data 1 to 7, when the data 0 is busy, is in a don't get state actually. So when we start operations of the eMMC bus, like when you do a power on mode, so it will be in the open drain and then it will be switched to the push pull mode. So this makes probing of eMMC bus makes it difficult, because when it is an open drain, it is not unterminated. When it is in a push pull mode, it's a terminated mode. When the switching takes place, there can be the probing solution is not very good, so there could be a lot of reflections. Okay. So that's why the probing becomes very, very challenging for eMMC interface. So during the boot mode and all the identification stage, so it will be in the open drain, and then when it is switches, normally in the boot mode, the maximum clock frequency is 400 kilohertz, and then it can switch to the higher data transfer mode. Depending on the need, it can switch to 25 megahertz, 50 megahertz, or 200 megahertz, so based on the need. So these are the different operation modes which are supported in eMMC. So these are the different bus voltages, like the eMMC, the backward compatibility, the legacy bus can operate on a SDR single data rate mode, and it can operate from 3.3 volt to 1.2 volt, 1 bit, and maximum frequency is 26 megahertz, and maximum data throughput is 26 megabits per second. Now, megabytes per second, because when it operates on an 8-bit mode. Now, all the way it can go to UHS-400, the current generation, that is the eMMC 5.1 specification. It is also backward compatible to high speed and the high-speed DDR mode HS200 and HS400. So in this case, the voltages are at 1.8 volt or 1.2 volt range, and the bus width is 4-bit or 8-bit, and maximum throughput what we can achieve is 400 megabytes per second. So that's the overall data throughput we can achieve with the eMMC interface. Now, how does the eMMC signal would look like when the signal can have a input low voltage, the VIH and VOL, these are all specified here. Because when you are doing the electrical characterization, so we need to have a clear understanding of how to measure VOH and VIL parameters. VOH is output voltage with respect to the device, and in this case, a write operation is a VOL, okay? And VIN, all the input and output, let me make it very clear here. The input and output operations are defined with respect to the device side, that is at the eMMC end. If you are writing a data or if you are sending a command to the device, it is an input operation. If you are reading the data or if you are sending a response to the controller, then it is an output operation. So the VOL needs to be measured at point different voltage levels at push, pull, and open drain. These parameters are defined here over here. So one has to characterize when they are doing it for electrical layer. So what is the VOH, VIL, similarly VIH and VOH parameters. Okay. These are the different electrical timing parameters one needs to measure, like for example, clock frequency, 26 megahertz and 52 megahertz in the high-speed DDR mode. Okay, we are not talking about here HS200 and HS400, so it is just up to high-speed DDR, that is 52 megahertz speed. Okay, and then we have a clock frequency identification mode. That's a 400 kilohertz frequency. That's when the open drain mode, FOD. Okay. Clock duty cycle needs to be measured, high time and low time, the rise time and fall time, and input parameters for the command data and with respect to the clock. Similarly, output parameters for the response and data with respect to the clock. So then we have to measure the setup time, hold time, and all these parameters. So for the different data rate, like 25 high-speed DDR, high-speed SDR, and backward compatibility, all these parameters needs to be measured at a go, and the results needs to be produced for the characterization purpose. So it involves measuring multiple parameters exceeding more than 25, and it can be a very time-consuming activity. Similarly, we have it for eMMC 5.0 and 5.1. So HS200, where the clock frequency is going up to 200 megahertz. And what is the period, the clock cycle distortion here? Because as the clock gets faster and faster, we also need to measure the duty cycle distortion, the sleeve rate, and the rise time and fall time of the signal, the clock load time, the clock rise time and flow time. So all these parameters needs to be measured for HS200, that is a eMMC 5.0, and also 4.51, I think, and then eMMC HS400 mode. So we need to measure all these parameters at a time. So overall, if you look at, so electrically, we need to make a lot of parametric measurements, electrical parameter measurement at different frequency. And now, in order to make this measurement, we need to identify the boot mode, and then we need to identify the high-speed SDR, DDR mode. Then we have to identify the HS200 and HS400 mode. And within that data, we need to identify which is the input operation and the output operation data, and then make all these electrical parameter measurements and apply the limits. Okay, so this is the comprehensive activity needs to be carried out when we do the electrical characterization of the host and device components. Now, this is how it looks like. If you look at the waveform, the clock will be toggling. So we need to make the measurement at different voltage threshold levels, like at VIH, VIL, VH, similarly for VOH and VOL. Now, we need to make, I just talked till now about how many different measurements we need to do. Now we are talking about how do we make those measurements at what voltage level for the input activity and for the output activity. Now, in order to make those measurements, first we need to measure the VIH values and VOL values, and then we can go ahead and make those measurements. So manually making those measurements can be very, very challenging. Now, these are the different challenges we have. Like the first thing is that how do we probe the signals, which is like an open drain and push-pull mode, operating in DC to 200 megahertz and single-ended signaling. And single-ended signaling with 200 megahertz DDR can be very, very complex because there is a lot of noise and ground bounce happening when there is a switching takes place. The probe needs to be very high quality for that purpose. Then we need to identify the input and output operation, as I mentioned, because there are different parameters needs to be measured for the input and output data, and identify the data rates. Like if you look at the boot operation of a eMMC and then going into the data transfer mode, it can start from 400 kilohertz, then can switch to 25 megahertz, then 50 megahertz, then 200 megahertz. So there is a need to identify in the acquired data what's the frequency at which it is operating, and then make the appropriate measurements on that. Also, you need to make the measurements or considering the lot of transition, waveform transition, in order to get the reliable result. Because if you just make a measurement using one clock cycle or two clock cycles, the data measurement may not be so dependable. So in order to make it, you need to capture the data for a longer period of time. So with a deeper record length of the oscilloscope, and then process that data to make sure that data is very consistent, and you can look at the statistical data. So it is also a burst communication, because like if you look at there is a one command and then the next command, there may not be any activities. So in order to capture all those large chunk of data, so we may need to have a longer record length in the oscilloscope, so which we can discuss that in a separate based on your requirements. Now, so what we offer for making electrical measurement solution is that we offer electrical measurement PGY, MMC, SD, SDIO software, which supports eMMC 5.1 and SD3.0 and SDIO 3.0 electrical validation and protocol decode software. Okay, this software runs within Tektronix, like current generation oscilloscope like MSO 5B and 6B series oscilloscope. And also it supports DPO 5000 and 7000 series oscilloscope and MSO 7000. It runs inside and automatically makes all the measurements and gives you the result. So when it makes those measurements, it will identify all the input operations, output operations, and different clock frequencies, data rates, and then it makes the appropriate measurement by binning the data in appropriate bins, and then making those measurements. So we also need to use a high impedance probe, because as I mentioned, the signals in unterminated and terminate mode depending on the mode of operation. So you can use Tektronix TPP 1000, that's a passive probe with 1 gigahertz bandwidth, or you can use Tektronix active probe, which is a 1.5 gigahertz in bandwidth. So these are the different combination which you can effectively use electrical characterization of the eMMC and SD interface. Okay. So we also support keysight, like in case of a keysight or at a LaCroix oscilloscope. The only difference is that the software, you may need to run it on a Windows PC and then acquire the data using the keysight oscilloscope and save it in a H5 file format, then read it on the software which runs in the PC, and then make all the analysis. So it's a little bit offline. It is not fully seamless operation. In case of a Tektronix, you get everything in one setup. But in case of a keysight, you can still, if you already invested in the keysight and you are being more comfortable in operation of the keysight oscilloscope, you can always run our software on Windows PC, and then make all those relevant analysis. So this is the software, the results looks like. So we have a, all the electrical parameters, it will make a measurement, and it will tell you in the acquired data what is the minimum value, what is the maximum, and the mean value. And it also will apply the appropriate limits to those measured parameters, and it will tell you whether it is a pass or fail. Okay. So this is a summary of the result, but if you want to go through into the more details and how the results, where it is failing, debugging purpose, we also provide something called detail view, which maybe in a short of time, I may not be able to show it now, but you can go through the detail view and you can see if some parameter is failed, where exactly it has failed in the waveform, and then you may able to identify what might be causing that, whether there is a reflection, whether there is a ground bounce, or whatever it is causing it, you can take a look at that also. And in the acquired waveform, if you want to look at the protocol decoding, you can just look at the click on the protocol view. It will do all the protocol, decode the protocol decode, and show you the results. In the timing view, it will show you the number of clock cycles to be between the clock command and response, and those parameters also it will display in the timing view. In the protocol test, it will tell you basically whether everything is in order as per the standard, right? Like whether the command is getting a proper response, whether data is coming proper, or is there any CRC errors in the data. So some of those checks for the protocol it will do and display it in the software. This is a very quick way of looking at is there any problem in the protocol layer. If you really want to go to the detailed protocol analysis and you want to capture it for a longer period of time, then you need to have a protocol analyzer, which is a more of a data domain equipment. Oscilloscope is a more of a time domain equipment, which samples the data at a very high speed, which is as per its requirement. And then it will capture a short period of protocol activity, and then it can just show you the results. Now, this is how the test setup would look like. I'm not going to give a demonstration live demo today. This is a Tektronix, one of the MSO 5204 oscilloscope. We are using a Tektronix passive probe of 1 gigahertz bandwidth. One of the important things what we need to observe is that the ground link, right? Because these are single-ended signals. eMMC or SD are single-ended signals. And if you use a longer lead wire, ground wire, we will see that lot of ringing on the single-ended signals. Now, in order to reduce those ringings, we need to use a very short ground lead. And Tektronix and also other test and measurement vendors provide small lead wire, which will enable you to connect to the ground point and making sure that they are also very short. So this is a simple setup which I'm showing you here, how it needs to be connected to the device under test to make sure that you are making a reliable measurement. Because many times it can so happen that your DUP is perfectly all right, but the way you are connected your probes to the test point, it can have a lot of overshoot and undershoot, and then there is a slew in the signal because the ground leads are not connected properly and the signals are not tracked properly, and it can give you the wrong electrical parameter measurements. So it's very, very important that you make sure you have the right test setup, making sure that the ground wires are short and test points are connected properly. And then the probes are also high impedance, making sure that they all work at during the open drain and push-pull operations. Okay, so if you have any questions, you can just post it in the chat box. Maybe I can take it up at the end of the session. Okay, so now this is a closer look. Just want to make sure, because I just want to make sure that, so here we are connected to the signal, and this is the small ground lead. It is connected immediately to the test points. Okay, so that's how we are made sure that everything is connected. Now coming to the eMMC and SDIO protocol analysis challenges. Like again, how do we probe this entire bus? When we want to do the protocol analysis, we need to monitor all the 11 signals. That is the clock, command, and D0 to D7 lines. So we need to capture all those signals and then make an analysis. So it makes it very challenging for us to make sure very challenging to connect all the signals appropriately. And also the other important part, we need to take the input probe impedance needs to be very high, and also it should support all the 11 lines. Okay, so we need to provide the proper solution for that. And protocol analyzers should have the following capabilities to address this. One is you should be able to decode the large data because you want to run the test cases for a long period of time. And also, like if you look at the command and response, between the command and response, there can be a lot of dead time. There is no protocol activity would be happening, but then you should be able to exclude that information from your protocol data capture and still monitor that in the form of a timestamp when there is no protocol activities are happening. But just acquiring the every data can just fill up your buffer size and make the software to run very slow. Okay. And also you should like to see the on-the-fly decoding and dynamically change the data because your data can vary from 25 megahertz to 50 megahertz, 50 megahertz to 200 megahertz. So data keeps changing. So which can also we need to keep track of the data rate changes and capture the protocol activity. Similarly, bus width, like right, bus width can vary from 1 bit to 4 bit to 8 bit. Again, we need to track that and we can capture that. And analysis of the protocol data for error. So we have to on the fly check for any errors because if you captured few gigabytes of data and that would have millions of command and responses and you have to manually go and find those errors, it can be very, very complicated and stressful. And also sometimes you need to capture the data at a specific event. You need to have a powerful hardware-based trigger capability so that you can capture the data at the right time. And then to look at the right information, you need a search and filter capabilities. So these are the different challenges one needs to address in eMMC and SDIO. So this is the product what we are offering. PGY, SSM, SD, SDIO, eMMC protocol analyzer. It also supports SD. It can go up to eMMC 5.1. That's our current and latest specification for eMMC. One of the features of this one is the continuous streaming of the data. So when the protocol activity is happening between the host and device, you can monitor it and you can continuously stream the data to the host computer hard disk drive. So your buffer size is actually limited by the free space available in your SSD or a hard disk drive in your computer. Okay. So that's one of the biggest advantage you have with the PGY SSM protocol analyzer. It can also do the protocol decoding for the command, response, and all those parameters. And it also has a simple and advanced trigger capabilities. And also you can have a custom protocol decoding and event view. You can do that. So we have one of the industry's best probing solution because as I mentioned, probing is the most complicated. If you do not use the right probes, it can load the DUT. P0512 is an active probe, which you can connect to the SIG. Then we also have a P5011 probes, which is an active probe head with a flying lead set, which gives you flexibility to solder these flying lead sets to the test point and access the signal. So then there is a micro SD card interposer and a SD card interposer for mainly probing the SD card interfaces. And we also the different DUT, we can provide a custom probing solution based on your requirement. So these are the different probing solutions. So now looking at the P5012 active probe, this is a probe cable with the flying lead set. You have an active circuit right at the probe tip. This probe tip has a isolation circuit at the front end so that the high-speed 200 megahertz signal which gets into this probe should not reflect back to the device under test. So we have made sure that the probe head, the probe tips are isolated from the device under test, and we are just tapping a portion of the signal and taking it to the protocol analyzer. So this will ensure that the signal integrity in the device under test, as well as we are able to do a protocol analysis without any challenges. Now, this probe is a P5011 probe, as I mentioned. This comes with the flying lead cables, which these flying lead cables can be soldered to the test point and connected to the probe module. So this probe module, what it does is it receives the single-ended SDR signal, and then it converts that into a differential signal and sends it over to the protocol analyzer to make sure we are able to do a protocol analysis for reliability. And there is an isolation circuit at the again at the flying lead wire, making sure that our test equipment do not load the device under test. So this was the SD micro and micro SD and SD card interposer. Again, what you see here is that one end has a small PCB, which is the shape of the SD card connector or the slot. So this will go into the SD card slot, and the signal will and you can insert your SD card on the SD card connector over here, and the portion of the signal is tapped and taken to the protocol analyzer for analysis. So this is a broad range of probing solution for eMMC based on your need. Like, sometimes you may have a test patch on your board. Sometimes you have a header pin. Sometimes you just have a SD connector or a micro SD connector. Depending on your based on needs, you can hook up our protocol analyzer to the device on the test, and you can make your all analysis without much challenges. Okay. Now, once we have these high-speed signals, right, 200 megahertz, they move from the test point to all the way to the hardware inside the protocol analyzer. And these signals are NRV signals, but they're not encoded so much. So the frequency components of these signals can be quite different. So because of that, the propagation delays for command, clock, and the data line can vary. Now, in order to address those two challenges, we have provided an auto-tuning feature within our protocol analyzer, where you can do the auto-tuning, run your data, and the protocol analyzer will try to identify the right sample point to check whether the CRC errors are minimum, and then it will set the cap values within our protocol analyzer so that we are sampling the clock, command, and the data signals appropriately without any problem. So this is the capabilities available in the software, in the hardware. And then we have different trigger modes, like you want to capture the data at a specific event, so you can use some of these triggering capabilities. Like we have auto-tuning, and in the auto-tuning, whatever protocol activity happens between the host and device will be captured. When you do a simple trigger, you can trigger on any of the commands or a response. In an advanced trigger, you can do a sequential triggers. And in the external event trigger, you can feed an external signal. When it toggles, it will trigger the protocol analyzer to capture the data. And similarly for write acknowledgement and write NAC, also we can set a trigger. And in case of a SDIO protocol, we can do an interrupt-based triggering also. So these are the different trigger features are available in the protocol analyzer. And now how much data we can capture, right? So there is an option to capture the data as much as you can based on the free buffer space available in your host system. But sometimes you would like to capture on a specific duration. So we have provided flexibility where you can go and specify the duration. Maybe it is 1 hour or 10 minutes. You can define the duration and you can capture that. And if you select the manual stop, it will keep on capturing till you go and physically stop the acquisition, and it will stop the acquisition of the data. And when you set the trigger condition, you may also like to see how much pre-trigger and how much post-trigger data you would like to see. So you can also vary this trigger position in your acquisition duration. Like if you set 1 hour is the acquisition and is a 40%, so it will capture maybe in a 60-minute, like the 40% of that is the pre-trigger data, and the balance will be the post-trigger data. So it will capture the information based on these settings. So you have a vendor commands, like as I mentioned, 6 bits are allocated for commands, and that gives you flexibility to have a 64 commands. And most around 40-45 commands are already defined out of that. and some of them are reserved, and vendors can define their own vendor-specific commands. When you do a vendor-specific command, Prodigy protocol analyzer provides a flexibility in the software where you can go and define what are those bits and what are the for those argument values combination, and then you can store that. When protocol analyzer encounters these packets, it automatically decodes that as per the vendor-defined command and displays the result for you. Okay. And here is the analysis. You can have it. So, like you can look at the command signal, the boot data also. Like in case of eMMC, when you power on, if it supports the boot data, it will pull the command line below for a few milliseconds, and that indicates that the device needs to transfer the boot data, and it will start doing that. So if the boot data is transferred, then it will start the initialization. So all these modes are supported in SSM protocol analyzer. I will show you the live demo of it. You can also look at the data blocks, okay? How the data blocks are connected and the CRC values within the data block. And like if there are any reports, like the reserved commands are present, and the commands without any response, you can see that if there is a CRC error in the command, you can observe. If there is a CRC error in the response, you can notify that. Also, if the command is getting a wrong response, so that is also can be notified. So you can directly search for them in the search and filter the capability of the software, and you can directly go to those locations. You can see exactly what's going on in the protocol activity. Okay. And then you have a powerful search and filter capability. So you can select a command, and you can define the argument values in each of those 38 bits, and then you can specifically search for or filter out or filter in the information. So then we have a summary where we will show you the protocol activity in a. This is more of a graphical representation of the operation. This is not exactly the timing information. It's just to indicate you that when in the entire acquired data, how the protocol operations are looking like when there is a, like here you can see there is nothing is happening in between, and then again after some time some operations are taking place on the command data and response activity. And at the beginning you can see there is a very intense activity. And what feature we have also is we have a flexibility to go and search for any of the packets and commands in this data also. Okay. So then we have a markers, delta, go to trigger position, and the listing of the window, jump to marker. This will make your whole debugging activity much more convenient and easy to use it. Okay. Then you can at the end you can generate a report. So this is overall what we have in terms of product. Apart from this, we have now eMMC tester products, and also the SD Express protocol analyzers. So many more storage protocol analyzers we have. So let me switch to the demo. Just give me a second. Okay. Okay. So this is the software which I'm actually using it right now and connected to my protocol analyzer. So I already made the connections here. Okay, connection is established. So we can do a live capture offline, like if you have a trace file, you can read it and analyze it. Like if you have an analyzer and if you have colleagues to analyze it in some other location, you can do that. And similarly, we have a different card types like eMMC, SD or SDIO. If you are capturing from a power on state, you can, irrespective of that, automatically it will recognize the different operation modes, it will acquire the data. But your DUT is already in a boot condition and it has, you want to monitor only HS400 information, then you can select HS400 and data width and it will power levels, and you can know what's the VDD level and what type of probe you're using. You can go and set it. Here you have the advanced setting, which I talked about, which you can use it. Okay. So then we can go and set up whether we want to look at the decoding of only command or command and data, or command and visual line, that is the busy information. Okay. Then the trigger settings we can do, like we can set the trigger on any command and so forth, or advanced setting we can do also. So let me set it auto, and you can define the capture. So let me go into a manual mode, and it will capture. It will keep on capturing. And I will just click on run. It starts capturing. Let me power on my device and the test. So the device started booting, and you can see here my command line is gone low, and boot mode is active, and boot data is started coming in, and now you can see the boot operations start taking place. Okay. So it will also tell you whether there are any errors in the data, and you can see it is continuously capturing and update is happening. Okay. So if you would like to see, when I'm acquiring the data accurate, the decoding is continuously going on. And if I would like to see what is inside my boot data, I can click on this, and I can look at each of the blocks, 512 byte blocks. If I click here, it will tell me if it is any CRC error. If there is any CRC error, it will be highlighted in red color, otherwise it will be in a blue. Now this is all like rising edge, D0P, D2P, these conditions. So this is the data block. Then we can look at the boot data. So boot operations are taking place. So we can resize the windows, and we can look at command 8, command 9, decoding we can see. And this is the extended register. If you want to look at the decoding of the extended, you can click on that data block. You can see here that data block is good. And we can go and also look at the analytics panel later on, decoding of this register if you want. And then now we can see here, it will switch to 51 megahertz. It will be a switch command actually. Somewhere here, you can say switch command. And here you can look at the decoding of the switch command argument. You can see here. So this will tell you what is happening over here. And then you can go and look at the data block. So if you go and look at this data block, we can see here both positive going and negative going edge, the data will be sampled, and if there are any CRC errors, it will be highlighted. So this will help us to identify the problems, whether there is a problem on any particular data line, and then if there is a problem in the positive going or negative going edge, that may give us some idea whether there is a problem in the rising and falling edge of the signal. Okay. So then we can go down, and you may see that it may switch to higher data rate. It's switching here to 114 megahertz, and we can look at the data blocks here also. So this is how a simple, so easy to use protocol decoding can take place, and we can look at the data the way you want it. So, and then we can stop the acquisition. Let's say we are done with the acquisition, and then we want to look at the analytics. And here we can see the CID register values, and all the errors which we talked about are reported out here. There are 27 times a command has not received CRC error. 2 times there are some reserved commands, and then there is a 1 CRC command error, command CRC error. Okay, and then we can look at command histograms, write histograms, and here we can see the time plots. So if you want to go back to the results, we can go here, and we can find that. And whenever there is a bus is going high or low, is busy, we can see here, like how much time it is busy here, the duration asserted. And if you click here, it will, then you can directly go to that location where exactly in the UI. So this is where the command 6 is asserted. Like for example, you see some operations are normally high. If you want to look at this one, you click here and they say go to the location, event location. It will take me to that location, and that will help you to identify why bus has been busy for so long period of time. Okay? And at the end, we can generate a report. As I mentioned, we can export this data. So I think that's all. I also had a presentation today. We do have a UHS-II protocol analyzer also, in case if you're interested. And apart from this, we have UHS-III, UHS-IV, UHS-II, and PCI Express protocol analyzers. So I think now I'll turn it over to Pranav, and if you have any questions, I request you to post it. Pranav, over to you.
Thank you, Godfrey. Thank you for the session. So we do have few questions. The first one being, what is the solution for probing ST and micro ST?
Okay. So for probing SD and micro SD, we have a interposers which are very flexible. One end of the interposer will go to your SD and micro SD slot, and other end you can in our interposer you can insert the card and you can carry out your protocol activity. And when this protocol activity is going on, interposer as a output, this can be connected to the protocol analyzer, and we can monitor the protocol activity. So we provide a very powerful solution which supports 208 megahertz speed.
Okay, thank you, Vasu. The next question is, what is the memory buffer size for the protocol analyzer?
Yeah, memory size is actually limited by by the host computer free space available. It can be in gigabytes. So actually, protocol analyzers support the streaming capability. You can actually acquire the data for a day or two, depending on your requirement. Make sure that you have enough free space in your host computer system for your analysis purpose.
Okay. The next question is, are Lecroy and Keysight oscilloscopes supported?
Yes, we do support Lecroy and Keysight oscilloscope in an offline mode. In case of Tektronix, we do that live in the Tech oscilloscope. You can store the waveforms we acquired from Tektronix, Keysight or Lecroy, and recall that in Prodigy software for analysis.
The next question is, does the PGY SSM SD protocol analyzer be used for electrical characterization of SD3.0?
Yeah, let me, okay, yeah, whether PGY SSM can be used for electrical characterization of SDIO? Answer is no. For electrical characterization, you need to acquire the data using a time domain analog instrument, that is oscilloscope, okay? So we provide a PGY, eMMC, SD, SDIO electrical validation software. You can use that software to analyze the SDIO electrical characteristics. Okay, you can make the measurement, compare it with the limit, and you can debug that. That is supported in the software, okay, but not in PGY SSM. And I also like to, I see one more question there. Do we have a PGY software compatible with Keysight? I think I already answered. We do have a software which is compatible with the Tektronix 68B and as well as UHS-II. Yes, we do. And we provide both node locked and floating license. And if you have a floating license, you can use it either of the oscilloscopes.
Okay. We have one more question. Do we need weak pull-up on the CMD and data for host controller? And also, the eMMC slave device contains pull-ups. Like, does the eMMC slave device contain pull-ups?
Okay, so yes, I think we can use the regular pull-up resistor. We really not seen much problems with the pull-up resistor. So we can use the pull-up resistor, and we are not seeing any eMMC slave device containing pull-ups. No, I think the pull-up resistors are on the board, not inside the devices. So you can you need to place them actually, yeah, between the host and device. It is a system level requirement. These are not inside the devices. You can use maybe 2.2 kilo ohm or resistor to pull up to the 1.8 or 1.2 volt range.
Okay, that's all for the question. Thank you all for joining us today. You can visit our website www.prodigytechno.com to see the full range of protocol analysis solutions. And you can always write to us at contact@prodigytechno.com for any queries you may have.
So thank you everyone. Have a great day. Bye now.